A todos, nós vamos dar início e eu vou passar a falar em inglês aqui para que o professor Geoffrey possa nos acompanhar. So, good morning, everyone. I just want to say that it's a great pleasure for us to host this short talk with Professor West at the Fórum of Interdisciplinarity. So this is a special edition, and I will ask Professor Anna to coordinate from now on.
Okay, thank you very much. Professor West, it's a great pleasure to have you here. I will say some words about his work. So Dr. West is considered for the time one of the most influent persons in the world, one of the 100 persons that is influent in the world in 2006. He has been working in the Santa Fe Institute, and he used to work in these multidisciplinary studies, that is, he's working with these complex adaptive systems that's applied to physical, computational, biological, and social environments. He's graduated in Cambridge and doctored by Stanford, and he's also member of Society of the American Physics Society, and he has been awarded with several prizes, like the Mercer Prize from the Ecological Society of America, the Weldon Prize, and the Glenn Award. And he has been working as a professor in the Stanford University in Los Alamos Laboratory. And one of the main work that he has talked about yesterday night was about his work with about the pattern of growth of the cities. And he used some very simple rules, and he has a theory about how they grow and how are the influence of, for example, the average income, how it works in the cities, how the size of the streets and dimension of the number of gas stations, how they are related with the size of the cities. It's very interesting. And he will talk with us in a very informal way. So, and then we will have some time for questions. So he will talk with us about 20 minutes, and then if you have some questions, we will open it for his answers, okay? And thank you very much again.
Thank you. Well, it's a pleasure to be here. Thank you for having me. I don't know. Oh, yeah, I have to use this. So I was, the main purpose of the visit here was to give a talk last night, a public lecture, which some of you may or may not have listened to, gone to, and I will refer to it a little bit, but you don't need to have gone to that talk to follow anything that I'm going to say in the next 20 to 30 minutes. But I was also asked to give this little presentation, and I wasn't too sure what to talk about, and it was suggested that I give a little bit of background to how someone that was trained in physics and worked, which was not mentioned really in this, I worked most of my career working in something called high energy physics, elementary particle physics, meaning the study of the fundamental properties of matter. I've worked a lot of quarks and gluons and dark matter and string theory and the Big Bang and all the rest of this wonderful stuff, which is very reductionistic. That is to do with what are the fundamental constituents and their interactions and so on. But in the last 10 to 15 years, my work has moved in exactly the opposite direction, and I have worked a great deal on questions already alluded to a little bit in biology, some sort of big questions in biology, which I'll talk about in a moment, and I talked a little bit about last night, And that led to this present project, which is to understand cities and to develop a science or a physics of cities. And part of that was motivated just because it's a very interesting scientific question, whether one can, in fact, have a science of something as complex and complicated as a city and an urban system. But more importantly, it became a passionate interest of mine, because I began to realize that the major problem facing society and facing, in fact, from my viewpoint, science and technology, is to understand cities, because the future of the planet is completely dependent upon urbanization. And anyone in this room that is a physicist will understand that when I remind you that we have been urbanizing at faster than an exponential rate. And an exponential rate is simply not sustainable. And the question is, can we make a smooth transition to some other state, and what kind of state would that be? Anyway, I'll talk about that in a minute, but I just wanted to just say a few words about how I got into this, how I made this strange transition from not just working on, by the way, not just working on quarks and gluons and string theory and the rest, but I was running a very large group of theoretical physicists at that time at Los Alamos, but also a large experimental group doing experiments at Fermilab, and also developing something that you may or may not have heard of, something called the superconducting super collider, which was this enormous accelerator that was to be built in Texas in the 90s, but was canned, was no longer funded during the Clinton administration. But I was very heavily involved in all of this stuff. And so the transition took place partly because of the failure, if you like, of the completion of the superconducting super collider, because at that time there was especially in the United States, there was a kind of quite a powerful anti-science kind of culture was developing. And it was anti-science, but it was primarily anti-physics. And within physics, it was primarily anti-high energy physics, elementary particle physics, because it was so expensive, for one thing. And the statement that we heard at that time, many of us, was the following, and some of you may be familiar with it, was that physics was the science of the 19th and 20th centuries, but biology will be the science of the 21st century. Now, it's very hard to disagree with that. That is almost certainly true, but I'm going to amend it in a minute, actually. But but there was something there was a corollary to that statement that usually was left unsaid, but implied, and occasionally in more private situations was said explicitly, and that was, the corollary was, okay, biology will be the science of the 21st century, and there's no need any longer to do any more physics. We know all the physics we need. And this, believe it or not, was said at places like the Department of Energy and so forth, which funds most of physics in the United States. So this was sort of amazing to me and to many of us. And in fact, I reacted by saying, yes, biology may well be the science of the 21st century, but it won't be a real science, meaning like physics, unless it incorporates some of the culture and some of the paradigm of physics, meaning that it should be principled, based on principles. It should potentially be mathematizable it should be computational, and it should be predictable. And I didn't know any biology at that time, by the way. I knew no biology, basically. But I felt that quite strongly. And that started me thinking, actually, about biology, and thinking that, okay, when I look at an elementary biology book, there's almost never an equation, almost never. And even in advanced biology books, except in certain fields, there's never an equation. And in particular, so I was about, at that time, I was in my 50s, about 50 odd years old. And I was beginning to age. And so there was a parallel phenomenon, okay? So here, there was this thing that somehow my field was being attacked. And at the same time, I was very conscious of my own physical aging. I don't need to describe to any of you in this room looking around what that means. You're all familiar with the consequences of aging. And it occurred to me that was a very interesting problem to try to understand. So one of the first things I did is looking in biology textbooks, because I had this idea that, my goodness, if I looked in an elementary biology textbook which describes all of life, there will be a chapter on aging and death, and it would explain what's going on in terms of aging, and it will have a little calculation in it where it will calculate why it is that the order of magnitude of life for a human being is of the order of 100 years. And I said in the lecture last night, if you were there, and I'll say it again in this room, that there's a precise, almost, prediction one can make in biology, and that is that everybody in this room will be dead in 100 years. Everybody. And some of us will be dead much sooner, by the way. And the question is why? Why is that? And first of all, why is it? And where does that number come from? So, so here was my thinking. If biology were a real science, there would be a calculation that would tell you about molecular dynamics and molecular time scales, because it's a puzzle. Molecular time scales are microscopic. How in the hell does that somehow scale up to be 100 years if you're a human being? Where in the hell does that come from? And if you read at that time, and you still read it now, the detailed discussions in gerontological literature, often what is said, well, it's genetic, it's in the genes, which from a physicist's viewpoint is kind of meaningless, because it doesn't say anything. Just say it's in the genes. Might as well say God willed it. It's not a very mechanistic explanation. So I was interested in a mechanistic explanation. So I decided, in an arrogant way, that, well, this is an interesting problem to work on. Maybe I can understand where this 100 years comes from. And by the way, at the same time, I also realized there was another very curious puzzle, and that is a mouse, which is made at a kind of a rough level, of exactly the same stuff as we are. Basically the same genes, the same cells, made pretty much the same, only lives for 2 years or 3 years. So what's going on here? Anyway, that was the problem I set myself. By the way, I was encouraged in my thinking by a very famous book, which most of you probably never heard of, but it's a very famous classic book of science called On Growth and Form by a biologist about 100 years ago called Darcy Wentworth Thompson. And he was a mathematician and a biologist, which you could be at that time. He was also a famous classicist, which, in fact, he was a Scotsman, and he was the president of the British Classics Association, as well as being a very famous biologist. And he wrote this book, which is a beautiful book, and he opens the book by saying that, this is about 100 years ago, he said that Immanuel Kant in the 18th century had said that chemistry is a science with a small s, lowercase s, but is not science with a capital S, because real science is that it's mathematizable, just what I said. That's what Thomson said 100 years ago. And he then goes on to say, well, in the intervening time since Kant, chemistry has become a real science. We have principles, we can calculate things, we do experiments and test them and so on. However, biology, he said, is still a science, but not science, because it has almost no relationship to mathematics. And his quest was, can we make a mathematizable biology? Okay. That leads, and I'm going to come back to this, to present day, where many of the problems, one of the great challenges in science is to deal with systems like life, but complex systems that are evolving and adapting. And so, of course, all of life is like that, but by extension, all social life, or psychological life, and so on. The question about those systems, which I will return to again in a minute, is that are they amenable to this physics way of thinking? They may be amenable to scientific thinking, but can they be put into a mathematizable framework? And that's a question I'll come back to in a moment. And by the way, going back to that statement, that question, or that statement about biology being the science of the 21st century, Stephen Hawking, at the turn of the millennium in 2000, was asked the question by, I think the question was, people say that physics was the science of the 19th and 20th century, biology is the science of the 21st century. What do you think about that? And he said he disagreed, because the science of the 21st century will be complexity. And that I do agree with. That's and complexity, by the way, and if I have time, I'll elaborate on that, but complexity is inherently multi, cross, and transdisciplinary. It involves many different areas of science, and I think the challenge in the 21st century for us is, to what extent can we develop a science of complex adaptive systems, and how do we somehow organize research and organize universities to accommodate to this somewhat different approach to science. That is, that it's a complement. It doesn't replace anything. It's simply expanding the horizon so that we don't all work in a highly stovepipe way on individual problems, etc. And again, I'll try to come back to that in a moment. But anyway, I started thinking about this, this problem of aging and mortality. And my thinking was that if you want to understand aging and death, you better understand living, and living means metabolism. And so I learned about metabolism, and it was at that point I discovered, I didn't discover myself, but I learned about these extraordinary scaling laws. And I just want to tell you a teeny bit about them for those that didn't go last night, because they're kind of extraordinary, and they lead to all kinds of interesting things, and they are a template for thinking about some of these questions that I raised. So the scaling laws are, the most famous was discovered already 70 years ago, and is to do with metabolic rate. And it was discovered that metabolic rate, that is the rate at which energy needs to be supplied to an organism to keep it alive, scales in an extraordinarily simple way across all of life. In fact, now we've extended it down, in fact, all the way to molecules and all the way up to ecosystems. And in terms of organisms, it covers 21 orders of magnitude. in terms of molecules, it goes 27 orders of magnitude. In terms of ecosystem, 40 orders of magnitude. And it's the same law, basically. It's absolutely extraordinary, and it is very simple. It is that the metabolic rate scales as the 3/4 power of mass, irrespective of what taxonomic group you look at. And for those 3/4 power of mass means, does everybody understand what that means? I don't want to leave people behind, but anyway, it's a very simple law, that's the point. But the thing that was amazing about that law is, first of all, it exists because we believe in natural selection, and that you would have thought that since everything evolved based on its history and its individual environment, in every subsystem of the organism, in every gene and every cell type evolved individually in a unique way. If you plotted any physiological variable, there would be, roughly speaking, very little systematic behavior, because each point represents history, geography, and so forth. So there's no, why would there be any tight correlation? But if I had flashed up a slide, you would see it's extremely good. And what is even more amazing, it's true, as I said, across all taxonomic groups. It's true for any physiological variable you care to measure, and any life history event. Physiological variable meaning, the rate at which oxygen diffuses across a membrane, or the length of your aorta. A life history event means how long you live, or how long you take to mature, etc. So all of these obey very simple scaling laws, and they all have a similar kind of exponent. That 3/4 is reflected in all of the exponents that occur. And so I started thinking about that and working on it, and I worked, and this is where the interdisciplinary thing comes. I then, there's this place called the Santa Fe Institute. So I'm going to, oh, you can't hear this. Please. Okay. There's this place called the Santa Fe Institute. So I'm going to now go off tangentially for a moment, which was founded about just over 25 years ago. Founded by a bunch of extremely distinguished Nobel Prize winners. There was Murray Gell-Mann, who discovered invented quarks, Phil Anderson of superconductivity, the condensed matter physicist, a man named Ken Arrow, who's a very famous Nobel Prize winning economist, and so on. So there was this small group of very distinguished people who had become concerned that the way the reward system had evolved in academia was that more and more, not just young people, but everybody was being forced to focus on one problem. Not just on one discipline, but on one problem within that discipline. And so many of the big questions, and especially those to do with societal questions, were simply not being addressed at all. And so they felt very strongly there should be one place on the academic landscape that is the complete opposite to the traditional structure of a university, namely there would be no departments and there'd just be scholars. It's kind of like one's image of a Renaissance university, I suppose. But so you would bring together anthropologists, economists, physicists, biologists, whatever, and they would all be together in the same hallways, and they would interact. And in fact, you would not want people who worked in their very specific area. That was the idea. And they put this thing together, and to their amazement, lots of people came out of the woodwork and said, I want to be part of this, I want to join in, and so on. So I'm not going to spend time telling you about it, other than that this thing was formed, it exists, and has been very influential in promoting ideas about interdisciplinary, transdisciplinary kind of work. And it was the place, because of that, and the kinds of problems that people started thinking about, it kind of formulated this idea that complexity, and in particular complex, adaptive, evolving systems were really something that we need to focus attention on. And in fact, just to give you a sense of things, in somewhere in about the year 1990, I guess, Murray Gell-Mann had this idea that there should be a program called Earth 2050. So here was someone who was working, like I was working at the time, in high energy physics, but decided this was an interesting problem, that we should start to think about global warming, which was barely, I mean, hardly anyone knew of it at that time. Global warming, the effects on the environment, and whether the planet as we see it today is actually sustainable. Now here's what's amazing about this, that he tried to get this program going, and here is a very famous Nobel Prize winner. He got as much funding as he wanted to work on quarks and gluons and string theory, could get no money to work on the question of the sustainability of the planet. And the response was, this is not a problem really suitable for academic research. No, this is just an engineering question. You know, it was very much dismissed. And he did get some money somewhere in the 90s. He got some money from a bank and from the MacArthur Foundation, little bits and pieces. But that died, that program died before the year 2000, which was too bad, because just at that time, everybody started to get concerned about global warming, suddenly became a thing. And now, I don't know about on this campus, but across the United States and across Europe, almost every university has a new building which says, you know, the Institute of Sustainability, the whatever, you know, all these kinds of things are now everywhere and so forth. So that was kind of interesting, and that was typical of what the Santa Fe Institute was doing. And you talked earlier about your son, I think, brother, working in a bank on something that has become known as econophysics, which is applying ideas of physics to try to understand the stock market and make lots of money. And so that was actually founded in large part at the Santa Fe Institute with people, not to make money actually, although some of those people did make money, was just to simply understand, can we bring a kind of physics perspective to understanding finance. So, so the Institute now is, covers a very broad spectrum of subjects, and it's primarily a visiting institute with a very small faculty, but working on these kinds of problems, quote, of complexity, meaning those which have enormous numbers of agents involved, like an organism or an economy, but also is continually evolving and adapting, and it has all kinds of emergent phenomena occur, all kinds of phase transitions and tipping points and so on. And the fundamental question is, can we really understand these systems, or is the best that we can do describe them, or to make just unrealistic models and so forth. So this is still an open question, but the work that I got involved with became interesting because what it showed was that underlying this extraordinary complexity is the most complex system probably in the universe, life. Underlying it were these extraordinarily simple laws just from the data. And the question was, how do you understand it? And I got involved with the Santa Fe Institute because there was a very distinguished biologist that had just moved, the dean here, or the ex-dean, is that the ex-dean? Yes. Had been at the University of New Mexico. And this person, Jim Brown, had just moved there. He had just been recruited there. And he had been interested in this, and we started working, and he'd been associated with the Santa Fe Institute, and we started working together on this. And the idea was that that this universality of this simplicity actually is to do with the underlying networks that sustain life. Some being macroscopic, like your circulatory system, but some being microscopic, like intracellular networks and so on. But it is that there's the mathematics and the principles governing those networks are the same as the idea, regardless of what the evolved design was. So I'm not going to talk about that now, but that proved to be extremely successful, and we understood and could derive all those scaling laws and much, much more. So the work has branched out into understanding, you know, questions of why we sleep, the aging, the question of aging and mortality, the questions even of the growth of tumors and so forth. So all kinds of things have grown out of this work. And then in more recent years, as was mentioned in the introduction, it was natural to ask, can it be applied to social systems, and in particular, can it be applied to understanding cities and companies? And that's what I talked about some last night, and I'm not going to say much about it here, other than, again, it required, obviously, if you want to understand a city, and you know, like I did, nothing about it to begin with, you've got to find the collaborations where the expertise comes to it, and that expertise has to be in the form of people themselves that are willing to cross the lines and learn the language. And I must say that it's always very easy to talk about doing interdisciplinary work, but I often liken it to a marriage, which is, namely, you have to make a commitment. You really have to make a commitment, because the other person will inevitably make you very angry and upset you by doing things when you I'm talking about my own relationship, of course. I've been married for 48 years, by the way, so I speak with some experience. But, you know, you have to make a commitment. You can argue and yell and scream. You love, you hate, you know, and all the rest of it. And you have children, postdocs, the students, and they have to be integrated. But you remain with that commitment. And you have to learn, most importantly, the culture and the language of the other person. And that was extremely difficult. I can tell you many times, I should tell you the way this worked for us was that we met. So I was running this big high-energy physics group at Los Alamos. Jim Brown was running this big ecology group doing field work down in Albuquerque. And so taking time out from that was already a commitment. But what we started by meeting Friday morning in Santa Fe, beginning about 9:30, and we would work till about 2 or 3 o'clock continuously. And he brought along a student, a man named Brian Enquist, who has himself now become a very well-known biologist. And we worked at the board, trying to explain to each other. I mean, both of these, I should say, both of these were, from my viewpoint, fairly mathematically challenged. So it required great patience on my part, and I knew nothing about biology, and I still don't really understand what a gene is, despite I don't know how many discussions and explanations. But so we spent an enormous amount of this time explaining, understanding, and exploring. And we did this once a week, every Friday. And that went on for almost 15 years. Still sort of goes on, not as much now because the city work took over. And it was tremendous. It was really a fantastic collaboration. It grew in several different, many people were added. But it was, and it was very, the first year was, as I say, extremely frustrating. And so if it's to be successful, from my experience and from watching the people around me with their own collaborations, because we have collaborations between an anthropologist and an economist, for example, or between a physicist and an economist, and so on. And you see the same kind of thing, that you require tremendous patience and commitment. So this work morphed into this work on cities, and at first it was simply analyzing data and then trying to develop a theory. And indeed, for those that don't know, it turned out that when we started gathering the data. Unlike biology, the data had already been gathered by hordes of biologists before us. But city work, no one had thought this in this way about cities. And so it was a matter of gathering data and seeing, do cities scale? This.
So now we are going to open for questions. Please, Professor Graff is going to make the first one, and then we are going to put the word with the audience, okay?
Usually I leave to others to make questions. And at the end, I cannot make my questions because time is always short. But this time, I want to make a first question. And I need a little bit of courage because I see in the audience some philosophers. But I will ask anyway. Professor West, I think I've learned that, I have been learning that perhaps the ultimate reality, I don't know if we should search for ultimate reality, but if there is any ultimate reality, I've been learning that perhaps it's in interactions at different scales. And I would like to hear what you would say about that.
That's a very interesting question. I don't know if ultimate reality, but certainly, you know, from a physicist viewpoint, I suppose it's impossible to think of something that is totally isolated and non-interacting, doesn't have a meaning other than as an idealized form. You know, there's an idealized form, but there is, for example, one of the things that we learned from quantum mechanics is that it only makes sense to talk about, you know, when you observe something, to recognize that the observer interacts with the object being observed and therefore perturbs it. So there's an intimate relationship, and that permeates all of science, really. I mean, even to the extent of the anthropologist going into a village to study the village, being there already changes the village, of course. So and how do we account for that? And that's much more difficult in anthropology than it is in physics, because physics, we have an equation now that tells us, you know, the equations of quantum mechanics. So in that sense, it's true that what we define anyway as reality requires interaction, and that means, by the way, that you know, an object which you think of as, you know, when you look at something as a point or as an object, its properties change with the scale at which you look at it. You know, that is, that if you look at it, if you look at an electron, you say there's an electron, but how you perceive it with a photon, with light, what you see depends upon the frequency of light. So there's that intimate relationship, and that has very powerful consequences for thinking about the unification of the forces and so on. So yes, in a way it is. I mean, of course it leaves open the question, by defining it that way, what are you leaving out? You know, maybe there's other things that are outside that framework. I thought what you were going to ask, by the way, in terms of ultimate reality, when you said ultimate reality, was the question of the role of mathematics. You know, that is mathematics, you know, from a physicist viewpoint anyway, at least my viewpoint, mathematics is, you know, one great mystery of the universe is that mathematics seems to be the language. You know, it's, as I often say, it turns out, despite 99% probably of the world believing that it's either Latin, Hebrew, Greek, Sanskrit, or Arabic, it happens to be mathematics, which very few people understand, which is extraordinary. So, but it looks like much of the universe operates that way. I mean, we can understand, you know, the Big Bang and the evolution of the universe and the Big Bang and the formation of galaxies and so on. Now, how far you can push that is not clear in terms of reality. Can you understand love and hate and, you know, what's happening in the Middle East and so on with mathematics? Probably not. So that's the whole question of how far can you push this framework in terms of complexity to be useful.
Other questions, please? It's better. Does anybody has a question? Please introduce yourself, because
So hello, my name is Aurelio from engineering. Thank you for your lecture last night. It was very good story. You're a good storyteller, and your enthusiasm is really important, I think. But you made a comment that made me think last night. Actually, you made several questions that you left unanswered, and maybe you could answer one of them here. I got a feeling last night that sublinear is good and superlinear is bad. Excessive growth is bad and unsustainable. I think that's what you tried to express last night. But we have the fact that life dies, collapses. Every life dies, as you said. But cities are very resistant. As you mentioned, we dropped atomic bombs in cities, and they're fine after a few years. So how come isn't there some contradiction in this, or can we try to explain how come cities are so resilient compared to other complex systems?
Well, actually,
she's fine.
most, actually, it depends what you mean by the system, of course, but yes, cities are resilient. So this brings up a whole, you know, there's a lot of questions in your one question. So I didn't, first of all, I put no judgment on good or bad on sublinear, superlinear, and so on. That's not a judgment question. It's simply that the biology, which is dominated by this sublinear behavior and this economy of scale, leads to a stable configuration in terms of growth. And that plays a very important role in the fact that life is, as a phenomenon, is very stable, very sustainable, I should say. It's very sustainable. And indeed, you know, the sequence is you have economies, you have this network giving rise to economies of scale, which then has the pace of life slowing down and has a stable configuration in terms of growth, and the system then dies and then reproduces and so on. And that's an extraordinarily sustainable situation. What has not existed, as far as we know anyway, on the planet until, you know, the last few thousand years, is this superlinear behavior, which comes from this feedback, you asking me a question, me thinking and going and so on. And if we were to stay around, we would invent something and so on. Well, that's what's led to all of this extraordinary phenomenon taking place over a very short time scale. And this is important, something I didn't emphasize last night. This happens, you know, in extremely short lifespan, lifetimes. And so we are extraordinarily innovative and evolving on relatively short time scales. Biology nothing is more innovative, of course, than life, but its evolutionary time scales are incredibly long. So it takes many, many generations to see any effect of that continuous feedback. Whereas because of this phenomenon that we all participate in, the social network phenomenon, the changes take place on the potentially on the time scale of a human life, and certainly of very few generations. So the thing about, the thing that gives rise to the resilience of cities is, and I don't, I can't explain to you the mathematics of the network, social network, is in fact the properties of the social network that encapsulates this feedback loop and gives rise to this open-ended growth. And that does, so it says there's this continuous open-ended growth. And one of the things that goes along with it, which I didn't touch on at all last night, and is very important for cities, is the fact that as the system grows, it becomes more diverse. That is, to be more specific about cities, is that the different kinds of jobs, different kinds of businesses continuously opens up. So if you look at the United States, the most diverse city in terms of different kinds of jobs is New York City, biggest city, and it systematically gets less diverse down to small towns in a actually predictable fashion, it turns out. And the great thing about cities is that what that means is that like an ecosystem is stable, so even though it has this sublinear behavior, it still is incredibly resilient because it reproduces. Part of its resilience is its diversity. The more diverse it is, obviously, because if a perturbation comes along, you have more opportunities to move into a different direction. So, the classic example in the United States of a city that was not diverse was Detroit, which was relatively, in this language, sort of not exactly one-dimensional, but very low dimensionality in terms of its business opportunities. It was almost completely dominated by the automobile industry. And so when things got tough, it was too big to make the shift quickly enough. So cities that have been very successful and which are highly resilient are ones that have the greatest kind of diversity. And by the way, something I didn't talk about last night because I didn't get time to talk to do it, was about companies. Companies represent the other end of the spectrum. Companies often start out being fairly multidimensional because they have new ideas, all kinds of products they want to try on the market. But very quickly, the marketplace forces a company to limit itself to a few products. And more, as that company gets very, very successful, it gets, instead of increasing its dimensionality, which a city does, it decreases its dimensionality, and this inevitably and usually leads to its collapse. And indeed, we've just done an interesting analysis to show all companies in the United States die. There's no, the average, the half-life of a publicly traded company in the United States, that means a company that's already on the market and has had some success, is 10 years. Just 10 years. And there are a few companies, of course, that are a few hundred years old, but they're all, but I'm afraid the analysis shows that everybody's going to die. So it's an interesting question. Can you have a theory of companies and predict when Google is going to disappear and Microsoft are going to disappear? Because they will. They will eventually both go. And it's kind of interesting to see when it will happen. And mostly it happens because of this lack of diversity. And to make it very clear, one of the things that is extraordinary about a city, and I can't speak about Brazil, and I'm sure it's true, but in a big American city, there are crazy people and homeless people on the streets. That's not necessarily good. I'm not saying that's good. But they represent a boundary for the rest of us. They kind of are the extreme of outliers. And they allow all kinds of ideas and things, in some curious way, all kinds of ideas to develop. And whereas in a company, there aren't any homeless, crazy people. They get fired. And, you know, and in fact, you know, it's been very classic, especially in the last 10, 20 years, in the United States anyway, the research groups have decreased, and people that don't sort of go along with the policy get thrown out and so on. And it's very, very difficult for companies to actually support that kind of diversity. And if they do, and there are cases where companies say, yes, really important that we do this, we're going to form this little group of outliers, we're going to think, they pay no attention to it. This is very typical. So I'm not sure I've completely answered, but that's the sense of the answer.
Any other question? Álvaro, introduce yourself, please.
Good morning. My name is Álvaro. I'm from School of Engineering. Also, again, engineering.
Engineering.
Yes.
As well. Yes.
So in fact, I would like to make a lot of questions, but I will try to synthesize in 2 dimensions. So you developed some model that in fact talks that the size of the city or the population is determinant to the characteristics of the city, or so I would like to know if you develop this model through time, so analyzed cities in centuries ago, so it's a very different environment, social and economical environment, and also if you developed this model in a geographical, so West Hemisphere and Eastern Hemispheres, different cultures. Yeah. So if you can speak about time and space, please.
Very good. Very good. Yes, absolutely.
Can I put a little bit, one more question that is related to this one? For example, did you model the cities that are inside this kind of countries that are dictatorial, that has dictatorial regime or something like this, and if it's different?
Yeah. So okay, very good. Good questions. Yes, yes. So 2 preamble statements first. First, were you there last night? No. No. So because I talked about this in a question last night, so I'll repeat it in a moment. Secondly, one of the challenges and difficulties of this work has been getting data, because what you asked is a very natural question, and you would love to have data on, first of all, you'd love to have data everywhere around the globe. You'd love to have data, you know, of, I don't know, France in 1800, and Mayan cities and so on. You'd love to have all of this. Sadly, amazingly, very little data exists. Despite the fact that much data has been collected, the trouble is either it's not useful in the sense that no one defined what they measured. You know, I'm talking about statisticians, I mean, people who kept statistics in the 19th century and so on. Or it's written, it does exist somewhere, but it exists in big leather books in basements somewhere, and no one has dug it up. So that's the background to this. So the data that we have used is almost entirely modern data. Some of it, we can't go back much further than about 1950, amazingly. It's just extremely difficult to get good historical data. But we've looked across the globe at, let's see, many European countries, of course, North America, several Latin American countries, including Brazil, Chile, Mexico, Colombia, we have China. Now it goes to your question. China, amazingly, China and Japan, and by the way, I want to make one tangential comment, which is amazing about China. First of all, China and Japan, well, Japan wasn't dictatorial, but it effectively was, of course, during the evolution and growth of its cities. So they satisfy exactly the same laws. But what I was going to say tangentially is that I didn't say this in talking about the companies, but companies also scale, it turns out. And they scale in this sublinear fashion, going to your question, and they die. But what is interesting, we have a Chinese collaborator who has data from modern China over the last 10, I think it may be as much as 15 years, whenever the stock market began in China, and amazingly, it scales, and it scales in a similar fashion to the United States. It's kind of amazing, actually, anyway. So this is a big challenge. So spatially, it's pretty good. Spatially, it's pretty good. The two major areas that we're missing are Africa and to some extent India, although we do have some data on India. But we do have one piece of work which is very suggestive and supportive, and that is, I was not involved in this, but a colleague of mine working at the Santa Fe Institute in an interdisciplinary collaboration with anthropologists and archaeologists, looked at data from a Mayan urban system in Mexico, a pre-Columbian Mayan urban system in Mexico, and using all kinds of proxies for, economic activity, pot shards and the size of plazas in towns and buildings and so on. I mean, you have to believe the archaeological, anthropological analyses, which is possibly questionable, but using those and then doing the same kinds of analysis and plotting them versus the estimated size, population size of those towns, it satisfies the same rules. So that was very satisfying, even though there's lots of methodological questions, obviously, to do that are outside our expertise, to do with that. But it is very frustrating. We'd love to have much more data to verify the spatial and temporal universality of these results. But so far, there are no major exceptions.
So we could stay for a long time talking with you, but unfortunately we don't have much more time because Professor West needs to leave. So we would like to thank you again for this wonderful talk, please.
I would like to thank Professor Anna for your coordination of our short talk, but very interesting talk. So I would like to assume the compromise of bringing you more of Professor West, and we'll invite you for a new project we have just started that is, I don't like the word higher studies, but it's we used to call that a project of higher studies. But it would be nicer to say nice talks and nice conversation, brainstorms, and so that's very nice. So it's really a pity that we do not, we should go on for a more ordered schedule and not stay in this chaotic discussion, very nice chaotic discussion. So we need order in the universe as well as we have all the brainstorm. And so it was very nice to have you here, Professor West, and we wish you a very good trip back. And I know, we know that you have a schedule in São Paulo and you have to leave early, so thank you very much for your time and your attention.
Thank you.